Hello, everyone. Today's topic is molecular geometry, which focuses on the VSEPR theory. Okay, so VSEPR, however you want to pronounce it, it's a weird acronym, but what it stands for is valence shell electron pair repulsion theory. And what it focuses on is the electron configurations of the molecules and what shape the molecule is going to take as a result. Okay. So, depending on where the electrons are, where the bonds are, you'll get different shapes. And remember, those shapes are meant to keep the electrons as far away from each other as possible. Because remember that like charges repel. So electrons don't want to be near each other. So the whole point of these bond angles is to keep the electrons as far away from each other, as well as maximize space, because the atoms themselves still have a particular size and they need to make room for those atoms. We call that steric hindrance when atoms run into each other. That's has to do with organic chemistry. You don't have to worry about that. But the whole point, this whole theory is focused on how the electrons interact with one each other when they're near each other. So in terms of doing problems, you just have to be able to understand and follow the three rules that go with it. And everything builds on one another. So the reason this is later on in the unit is because before you can do any of this, you have to know how to draw Louis structures, which is why those first couple of days were centered around learning how to draw these things. Because if you don't know how to draw them, then these rules will not make sense to you. Okay, so let's go through the first rule. So VSEPR, figuring out what shape something is just by these number codes. And the number code is you get the number code through these rules. And the first rule says that the first digit is the total number of electron domains around the central atom. And what is considered a domain is a domain is considered either a bond or a lone pair. And note that it says double and triple bonds only count as one domain. So let's look at this first one. They have the numbers here for you so you can see what the first digit is supposed to be. So how many bonds and low pairs are around the B? The B has 1, 2, 3 bonds and no lone pairs. So the total number of bonds and lone pairs is 3. If we look at the XE here, how many bonds and lone pairs does it have? It has 1, 2, 3, 4 bonds and 2 lone pairs. Total number would be 6. And here, how many bonds and lone pairs does oxygen have? It has 2 bonds. Now, the reason it says 3 is because technically that is not drawn correctly. There should actually be 2 electrons that are here. It should have a lone pair because the oxygen won't be happy without it. Okay, and technically these over here should have lone pairs as well. Now I'll actually draw them so you don't get confused. So this is what it should look like if they actually had everything on here properly. So this is what you should have in theory, okay? So this would be 3 bonds, no lone pairs. This is 6, it has 4 bonds and 2 lone pairs. And then this is 3 because it has 2 bonds and 1 lone pair. Again, it says double and triple bonds only count as one domain, okay? So this is one domain, this is 2 domains, and then that would be 3. So that's the first digit. The first digit tells you what they call the electron domain geometry, okay? So if the first digit is 2, you get a linear shape. If the first digit is 3, they get trigonoplanar. If the first digit is 4, you get what they call tetrahedral, so on and so forth. So that very first digit is going to give you the electron domain geometry, or EDG for short. So when you're looking at the practice problems for this section, I have you doing the VSEPR number, geometry, hybridization, and bond angle section. For example, look, this one says, what is the electron domain geometry, or EDG? That's what they're referring to. So it is the first number, okay? The first number tells you the EDG, okay? And let's go through one example here. It says, what is the electron domain geometry of CH4? If we draw CH4, it would look like this, okay? C, CH. Okay, you can draw all the four of them. How many electrons are we working with? Because remember, you got to follow the rules to know how to draw it. How many electrons do we have in our bank? Carbon gives us 4. Hydrogen gives us 1, but we have 4 of them, so that's 8 electrons. Each bond is 2 electrons. That's 2, 4, 6, 8. So we used up all of our electrons. The carbon is happy. It has 8. Each hydrogen is happy. They only want 2. So if we follow the rules of this, the first number is supposed to be the total number of bonds and lone pairs, and that'll give us the EDG. How many bonds are on here? 4. How many lone pairs are on here? 0. So what is the first digit? The first digit is 4. And if the first digit is 4, our shape is tetrahedral. Okay? So for CH4, the EDG would be tetrahedral. Okay? This one, how many electron domains does H2O have? So it should be referring specifically to the oxygen. So if we look at the oxygen, how many bonds and lone pairs does it have? It has 2 bonds and 2 lone pairs, so the answer is 4. And then the answer again would be C, tetrahedral. Okay, so those are some examples. And I'll move on from here. Actually, no, this is a good example to look at. So how many electron domains does CO2 have? So we're going to be looking at the carbon because the carbon is the central one. This time, we only have 2. Okay, these are double bonds. Remember, double bonds still only count as 1. So this is 1 domain, this is 2 domains. There are known lone pairs on the carbon. So this one would be 2. And then it's going to ask us what is the EDG. And if you go back up to your list, 2 atoms is linear. Okay, so then if we were to draw this molecule, it would be in a straight line. Okay, so this one would be A, linear. The second digit is the number of bonds only. Okay, the second digit is the number of bonds only. The third digit is just the lone pairs. So the easiest way to remember this is the first digit is the bonds and lone pairs. The second digit is just the bonds. The third digit is just the lone pairs. Okay, but let's just focus on rule 2 for now. Rule 2 says what are the number of bonds or bond domains around the central atom again. Okay, the second digit is the total number of bonding domains only, so it does not include lone pairs. So the second digit for this again would be 3. There's only 3 bonds and no lone pairs. This one, there are 4 bonds and 2 lone pairs, but the lone pairs are not included, so it would just be 4. And this one is 2. Again, let me draw the dots so we can be on the same page. This is what it's supposed to look like. And this one would be 2 because we're not including the lone pairs. You have 2 bonds. First digit is the bond and lone pairs. Second digit is just the bonds. The third digit is the total number of lone pairs. Okay, so this one would be 0 because there's no lone pairs on it. This one would be 2 because it has 2 lone pairs. And this one would be 1 because there's only 1 lone pair. Okay. And then to get your final shape or your MDG, okay, notice these problems are looking for EDG. There's also one that's going to ask you for the MDG or the molecular domain geometry. The MDG are these, okay? The molecular geometry is what you get once you get your total number code, okay? So this is 330. 330 is trigonoplanar. So this molecule would be trigonoplanar. 642 would be square planar. This molecule would have a square planar shape. And 321 is a bent shape. So this one would be considered bent. Okay, now the difference between the EDG and the MDG, let's look at it now. Okay, so if you look at the EDG, let's go back up to the top where it talks about the electron domain geometry. For a 3, 3 is supposed to give us trigonal planar, right? So if we go down to here, the first number is a 3. So the EDG we expect to be trigonal planar, but the shape that we end up getting is bent. The reason for that is because of the lone pairs. So here, this right here would be ozone. This is what ozone would look like. This is the 3-2-1 that we see above. So what the lone pair does, so again, the first number tells you how many bonds and lone pairs, and then the second two basically tell you the distribution between pairs and lone pairs, or bonds and lone pairs. When you have a lone pair, the lone pair takes up more space than the atom does. So whatever atom would be here, the lone pair would take up more space, okay? So because it takes up more space, it forces the angle to change a little bit in order to make room for it. Because remember, the electrons want to be as far away from the other bonds as possible. So it changes the angles of the bonds. But if you look, the shape is fundamentally the same. If this lone pair was replaced by an atom, you'd go back to trigonal planar. So the first number, which tells you the EDG, tells you the general shape, but these atoms can be replaced with electrons instead, basically, is what it's saying. So let's say the first number was 4. If the first number was 4, you'd have a tetrahedral shape. But if one of the atoms becomes a lone pair, that's now replaced, and you now have what they consider to be trigonal pyramidal. And if you instead have 2 lone pairs, it now takes a bent shape. And this is water. This would be a water molecule, 1 oxygen, 2 hydrogens, and 2 lone pairs. So this would be an example of water. And you have a bent shape, but if you replace the electrons of atoms, you get to the original tetrahedral shape. So think of this, the first number is going to give you the general shape, and then the second and third digits are going to tell you how many bonds you have and how many lone pairs you have. So for every set of lone pairs that you have, you're going to replace one of the atoms with some electrons. Basically is what's going on. So that's what the lone pairs end up doing because they take up more space. And then there's one more thing to consider, and then they're just showing you the example for if you have 5 trigonal bipyramidal, how they get replaced slowly by electrons. The last thing we need to discuss is what they call hybridization, and this is the last thing you need to see before you can answer all of the questions on the worksheet. I know this theory is a little complex, but as long as you follow the rules, just go through it step by step. But as long as you follow the rules, I promise you'll get through it. Last thing we need to discuss is hybridization. Why is hybridization even necessary? So when it talks about hybridization, what they're talking about is combining different orbitals. So for example, we can combine this s orbital with this p orbital, and we call that sp hybridization. But why is it necessary? So carbon, as I previously told you, is always going to want 4 bonds. It's always going to want 4 bonds, whether they be all single or some of them be double. Okay. In order to make those bonds, we need some more electrons in this p orbital. It only has 2 electrons in the p orbital, so it only can pair up 2 of them, but it ends up getting 4 bonds. How is that possible? The only way that's possible is by making a hybrid orbital that now has 4 electrons that can be paired, okay? Every bond forms a pair. If I only have 2 electrons to pair, I can only form 2 bonds. So that is why the hybridization is necessary. So what's going on is we're combining the s and the p and making a sp hybrid orbital. The number of p orbitals you need is what's going to change this number right here. In this case, we're using all 3 houses from the p orbital. The p orbital can hold 3. Okay, remember from the boxes, the p would have 3 boxes. We're using all 3 boxes. So because we're using all 3 boxes, This is sp3 hybridization. And now the carbon can have the 4 bonds. Okay. The easiest way to know what type of hybridization you're going to get is just by looking at that first VSEPR number. Okay. It says here to predict the hybridization, you just have to look at the first VSEPR number, which is the number of bonds and lone pairs around the central atom. And remember that double and triple bonds still count as 1. So in this case, that first number for carbon would be 4. It has 4 bonds and 4 bonds and 0 lone pairs. So that first digit would be 4. So we have 4 domains. 4 domains means we need sp3. Okay. This one again has 4 domains. 3 bonds and 1 lone pair. That's 4 domains total. So you get sp3. When you get into double bonds, remember double bonds count as 1. So this is 1 domain, this is 2 domain. So 2 would be just sp. Okay, so you're always going to need the s. The s covers 1. When you have 2, that means you need 1 p. When you have 3, you need 2 p's. When you have 4, you need 3 p's. So basically, if you have a 2, it's sp. If you have a 3, it's sp2. I'm sorry again, drawing stuff with the mouse is kind of hard. And then if you have 4, it's sp3. If that first digit, you just have to look at that first digit. If that first digit is 2, it's sp. If it's 3, it's sp2. And if it's 4, it's sp3. Okay, and let's do one of these example problems before we get into the homework or the assigned work. Okay. I don't want to do number 54 because number 54 requires me to draw all of these, which would take too long. So let's do 55. 55 says, what would be the hybridization found on the O in OF2? So we have to draw OF2. How many electrons are in our bank? It's the first thing. We have 6 from the oxygen, and we have 1 oxygen. And then we get 7 from the fluorines, and we have 2 of them. Okay, so this would be 14 plus 6, which gives us 20. Okay, this would be 20 electrons. So now let's draw it. The oxygen is less electronegative, so the oxygen is going to go in the middle. Let's draw our fluorines. Okay. Let's put our dots on the outer ones first, always. Okay. How many electrons have we used up so far? We've used up 8, 16. We have 4 left. The fluorines are happy. The oxygen is not happy. It only has 2 bonds, so it's 2 4 electrons. It needs the other 4. So we have 8 here, we have 16 here, 17, 18, 19, 20. So we've used up all 20. This is happy, and the oxygen is happy. Remember that the bonds are shared between them, and a bond counts as 2 electrons. 2, 4, 6, 2, 4, 5, 6, 7, 8. 8 on this one and 8 on this one. So they're all happy. Okay. So what is the first VSEPR number? Remember, the first VSEPR number is the number of bonds and the number of lone pairs. Okay. So we have 1, 2 bonds and 2 lone pairs. So that first number is going to be 4. And if that first number is 4, the hybridization we need is sp3. So the answer would be C. Okay, the answer here would be C. So now let's do some of the classwork. But let me get up to the rules so we can reference them when we need to. Okay, I'm just coming back up here because I want to make sure I point these things out as we go through it. Okay, So I'm going to do number 1 in the classwork and number 4 in the classwork, since they're the ones that have some of the more complex stuff. So see, 2 and 3 only go A to D. 1 and 4 go up to F and G. 5 also goes up to G, things like this. I want to make sure that I cover everything that you're going to potentially see. Okay? So let me do number 1. Let's do number 1. N2F4, which we have seen before. And I'm going to scroll to the top to draw it for us. Okay. So A says, what are the VSEPR numbers around either nitrogen atom? So there are 2 nitrogen atoms. So there's going to be 2 central atoms to work with. So let's draw what we're working with here. We are doing N2F4. So how many electrons are in our bank? Okay. We have 7 electrons from the fluorine. I'm going to try to save some time here. I'm going to go through this a little faster. We have 7 electrons from the fluorine. We have 4 of them. 7 times 4 is 28. You get 5 from the nitrogen. You have 2 of them. 5 times 2 is 10. 10 plus 28 gives you 38. Okay. We have 38 electrons in our bank. Okay. 38 electrons in our bank. Now let's draw what N24 will look like. So nitrogen, 1F up top, 1 here, 1 here, 1 here. Okay, go through the dots again. Remember, put the dots on the outer ones first. Boom, 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 boom. So, how many electrons have we used up so far? 8, 16, 24, 32, and then the bond in the middle here makes 34. So we've used up 34 of our 38. We have 4 left. With those 4 left, how many does each nitrogen need? This nitrogen has 2, 4, 6. This nitrogen has 2, 4, 6. So each nitrogen needs 2 more. So now we've used up our 38, and everyone is happy. Fluorine has 8 electrons. Each fluorine has 8 electrons, and each nitrogen has 8 electrons. So now everyone is happy. So what A asked us for, A wants to know, what are our VSEPR numbers? The first number, again, the first number is just the number of bonds and the lone pairs. Okay, the first number is the bond and lone pairs around the central atom. In this case, we're looking at nitrogen. Okay, so if we look at nitrogen, either one, it'll be the same for either of them. We have 1, 2, 3 bonds and 1 lone pair. So that first number is going to be 4. Okay. The second number is just the bonds. Okay. The second number is just the total number of bonds. First number is both bonds and lone pairs. The second number is just bonds. So if we're looking at just bonds, it would be 3. And then the third number is just lone pairs. The third digit is the total number of lone pairs around the central atom. Okay. So a quick way to check your work, these 2 numbers right here, okay, the second 2 numbers should add up to the first one. Okay. The second 2 numbers should add up to the first one. And 3 plus 1 is 4. So we're good. Okay, but this is both lone pairs and bonds. This is just bonds. This is just lone pairs. Okay, so these 2 should add up to the first number. So A asks us, what is the VSEPR numbers? And those are your VSEPR numbers. B asks us what? B asks us for the EDG of which one? It asks us for the EDG around either nitrogen atom. So remember EDG, electron domain geometry, that comes from just the first number. And you guys can reference the slides. I don't expect you to memorize this. Look at the slides. The EDG, if it's 4, would be tetrahedral. Okay. We're asked for the EDG of nitrogen, and the next one's going to ask us for the EDG of fluorine. So let's do the nitrogen real quick. So this would be tetrahedral. Spelling will be kind of difficult here. Okay. Jesus. Tetrahedral. Okay. Tetrahedral. It's hard to spell with this mouse. I'm probably. You guys get the idea. Tetrahedral. Okay. First one for 4 would be tetrahedral. C asks us for the EDG of fluorine. So if we let's pretend that fluorine is now my central atom. The first digit is again the number of bonds and lone pairs. So if we do that, how many lone pairs do we have? We have 1, 2, 3 lone pairs. How many bonds do we have? We have one bond. So the lone pairs plus the bonds would be 4 again. So it would be the same as nitrogen. So the answer would be the same as B. Okay, this is the same as B. Same as B. Okay, in this case. Okay, because the number is the same. You see that. Okay, the first number for here would be 4, just like for the nitrogen. So it would be the same EDG. So C would be the same as B, which is tetrahedral. Okay, so now let's do D. D, I believe, is asking us for the molecular domain geometry. Yep, what is the MDG? The MDG comes from the table. Okay, so this right here, the MDG comes from the table. So we are looking at 431. 431 would be trigonal pyramidal. I'm not even going to bother trying to spell that. Well, no, I'll write it. I'll write it shorthand, okay? So this would be, just to save time, this would be tri pi, okay? This would be trigonal pyramidal, okay? 431. Just go to the table. What is 431? 431 is trigonal pyramidal, right? Well, E. What is E asking us? Let's do E. E is asking us for what is the hybridization? The hybridization, you just have to look at the number in front again. Let's scroll down to hybridization. Hybridization, all you have to do is look at that first number again. And remember, just write this down. 2 is SP, 3 is SP2, 4 is SP3. So the number is 4. So because the number is 4, we are going to be looking at SP3. And F is asking us to look at bond angles. The bond angles, again, I do not expect you to memorize. Look at the slides. So we have trigonal pyramidal. Scroll down to your shapes, which would be after rule 3. So it starts talking about the shapes right after rule 3, and it goes through each of them. So we are looking at the first number would be 4. So remember that EDG, this tells you the shape. So the EDG would be tetrahedral. So look at the tetrahedral one. And in this case, we are at 431, which is trigonal pyramidal, which gives us a bond angle of 107. And remember, the reason the bond angle changes is because these electrons take up a larger amount of space. Okay, so this is 431, which is what we have. So the bond angle would be 107. Okay, so F would be, whoop, Ah, dang, I clicked out of it and I just erased everything, didn't it? Yep, sure did. Okay. F here would be 107. Okay, this is 107. If you want to see what I just had up there, please rewind. It would be kind of difficult for me to go back and do all of that again. Okay, so your final answer here would be 107. Now let's do number 4. Number 4, A, what are the VSEPR numbers? So before we do that, you got to draw it out. This is CO3 minus 2. Okay, remember that. This is minus 2, so we have 2 extra electrons. Each carbon gives us how many electrons? It gives us 4. We have 1 of them. Each oxygen gives me 6. We have 3 of them. 6 times 3 is 18. 18 plus 4 is 22. And then we have these 2 extra ones. 22 plus 2 gives us 24. So we have 24 electrons in our bank. Let's draw our molecule. You have carbon with 3 oxygens. We've seen this one before. This was in one of your other assignments or one of the other sections. Okay. This is going to require a double bond, if you remember. So I'm going to draw the double bond here. It doesn't matter where you draw the double bond at, okay, but I'm going to draw it here. Okay. One of them is going to need it. If you remember from this, actually in the day 5 video, it goes through it for the resonance. This is actually one of the ones we have to draw. This one does have resonance structures, but it doesn't matter which one you use. If you count them up, we have 8 here, we have 16 here, we have 24 here. So we've used up all the electrons. Each oxygen has 8, so they're happy, and the carbon has its 8, so it's happy. Okay? And let me actually draw this a little better so people don't get confused. Let me space that out just a little more, just so I don't want anybody saying they were confused. So that's a bond, and that's a separate molecule. There you go. And then let's just draw the dots. Okay. A asks us for the VSEPR numbers. Remember, the first digit is the number of bonds and the number of lone pairs around the central atom. Our central atom is carbon. How many bonds do we have? Remember, double bonds still count as 1. So this is 1 bond, this is 2 bonds, this is 3 bonds. Okay. First number is 3. Okay, the second number looks at just bonds. So how many bonds do we have? Again, we have 3. And the third digit looks at just lone pairs. Carbon does not have any lone pairs on it, so this would be 0. Okay, so A would be 3, 3, 0. B. B asks us to look at, I'm pretty sure it's the EDG of it. What is the electron domain geometry around the carbon? Okay, so go back to your slides, go back to the EDG section, electron domain geometry. If we have 3, we have trigonal planar. Okay, and I'm going to shorthand this for the sake of time. This would be triplanar. Okay, triplanar. That's what that one would be. C and D asks us to look at the oxygen. C and D, well, C is what is the EDG around a single bonded oxygen. So if we look at one of the single bonded oxygens, we have 2 of them, what would be the EDG of it? The EDG is based on the first number. The first number is the bonds and lone pairs. So if you look at these, we have 1 bond and 3 lone pairs. 1 bond and 3 lone pairs. So that first number would be 4. And 4 gives you, if you go back, 4 is going to give you tetrahedral, okay? 4 is going to give you tetrahedral. D asks us to look at the double bonded oxygen. If you look at the double bonded oxygen, you have 2 lone pairs and 1 bond. So that would be 3, which would give you the same answer as part B, which is the trigonal planar. Okay, this would be trigonal planar. That's C and that's D. C and D ask you to look at the electron domain geometry. C is for single bonded and D is for double bonded. Okay, so now we can move on to E. E says, what is the molecular domain geometry? That is, you get that from the table. So let's do E real quick. You get that from the table. Whoa. E. Okay, so we have to look at our VSEPR number. What is our VSEPR number? Our VSEPR number is 330. Go back to your table. 330 is what? 330 is trigonal planar. So because we don't have any lone pairs, the shape is not going to change. Okay, look, so you have 330 and you have 321. If one of our atoms was instead a lone pair, it would take a bent shape. But we have 330, which gives you trigonal planar. So this is the same as the EDG in this case. Basically, if you do not have any lone pairs, the EDG is going to be the same as the MDG. Again, if you do not have any lone pairs, your EDG is going to be the same as your MDG. So let's go to F. F asks us to look at what is the expected hybridization. What is the first digit? The first digit is 3. If you go back to hybridization, the one that you get is based off of that first digit. 2 would be SP. 3 is SP2. That's what we have. So you put here SP2, and I'm pretty sure G is asking for bond angles, if I'm not mistaken. Yes. What would be the expected bond angle? And again, just look at the slides. So go to the bond angle section, which is right after Rule 3. Rule 3 is here. Scroll down. We have a 3 in our first digit, so we're looking at the trigonal planar section. And then we do have 330. 330 would be 120 degrees. So this would be 1, 2, 0. Okay. So that is 1 and 4 for the classwork section. 2 and 3, the rest of them, some of them don't have as many sections. It's just about a little bit more practice. Okay. If you have any questions, again, you can ask them. You guys can work with each other. I know some of you guys communicate with one another. You can help each other out. If you can post comments and ask each other questions. You can text each other, however you guys want to do it. But I'm not expecting you guys. You don't have to work alone. Again, if you want to communicate with each other, you're more than welcome to do that. But again, if you have any questions, ask. Just follow the rules as best as you can. Just go through the slides, follow the rules. As long as you do that, I promise you, you will get through it. All right. I wish you the best of luck. Enjoy the rest of your day.